In this video, we'll use the graphs of two equations to solve an equation and two inequalities in one variable. Note that on my screen I'm only showing parts A and B, but parts C and D will be covered at the end of this video. To start, we're given two graphs, y1, which is equal to x squared plus 2x minus 1, and is shown in red, and y2, which is equal to negative x squared plus 3, and that's shown in blue. The first thing we want to determine is how many times do these curves intersect, and what are their points of intersection. After that, we'll use the graph to solve the equation x squared plus 2x minus 1, which is equal to negative x squared plus 3. Note that underneath this graph, we're told that an interactive version of this graph can be found, and then the link on Desmos is given. So I'm going to go over to that interactive graph before we get started. What I have on my screen now is this interactive graph. And note that these 2 points can be animated along each of these curves. So let's watch as they move, and there. And so these points are moving along each curve, and what we're seeing with this interaction is where the 2 curves intersect. So I'll try and stop it near there. Roughly, oh, I missed it. Let's try the other one. So as we can see, as the point moves along, there are 2 places where these curves are intersecting. What we'll look at after this is where the y values of one curve are larger or smaller than the y values of the other curve, and seeing those points as being higher or lower will be really helpful. So the first thing we're focusing on is where these 2 curves intersect. And I can see on this graph that right about where x is 1, these 2 are going to intersect. So they're right about at x is 1. When x is 1, those 2 curves will intersect. And then looking at this other point, I can see that where x is negative 2, those 2 curves are intersecting again. So let's go back to the graph in our notes. And I have the same graphs here, and I'm going to label these off. So this point of intersection, let's look at this first one. It's at the point 1, 2. Then I'm going to label that with the point 1, 2. And this other one, where x is negative 2 and y is negative 1, I'll label as negative 2, comma negative 1. So the first thing that I need to answer here is how many times do these curves intersect? So these curves intersect 2 times. At the points negative 2, comma negative 1, and 1, comma 2. So the next thing we're going to do is use the graph to solve x squared plus 2x minus 1 equals negative x squared plus 3. Notice that this is an equation and it only has the variable x. We've used these 2 equations in 2 variables to find where these intersect, but our solution is going to be a value of x because this is an equation just containing x. So the x values that make this equation true will be our solutions. So the solutions, or this, let's state this as where this equation is true. This equation is true when x equals negative 2 or x equals 1. So the solution set is the set of x such that x is equal to negative 2 or x is equal to 1. That's full set builder notation. I could also write just a short set notation, which is a curly brace, negative 2, comma 1, showing that all solutions to this equation are negative 2 and 1. So let's do a quick check and see what this looks like. I'm going to check the value of 1 as a solution, and I could do the same thing for negative 2, but I'm only going to check where x is 1. I'll plug in 1 into this equation. So I'll get 1 squared plus 2 times 1 minus 1, and I'm checking, does that equal the negative of 1 squared plus 3? So simplifying this left-hand side, I'm going to get 1 plus 2 minus 1, which is 2. And simplifying the right side, I'm going to get negative 1 plus 3, which is also 2. So what I can see is that this 2 equals 2, those were my y values. So those y values were the same when x was 1, and 1 is my solution there. We're now going to use these same graphs to solve x squared plus 2x minus 1 less than negative x squared plus 3. Let's take a moment to look again at our interactive graph. To determine where x squared plus 2x minus 1 is less than negative x squared plus 3, we're going to look where that red curve is lower than the blue curve. So starting this animation, let's look at this. And we can see that at some point it's higher, then they're equal, and then the red curve is lower. And so what I can see here is that starting at x equals negative 2 and continuing on to where x is 1, that red curve is lower. And then after 1, the red curve is higher. So let's go back to our notes and draw some things on our graph. So we're going to highlight the portion where that y1 equal to x squared plus 2x minus 1 is less than negative x squared plus 3. And so I'll highlight this portion of that red curve. And then down below, I can see that from negative 2 to 1 is where it occurs. And I'm going to transcribe this down below that grid. And one other thing we want to note is that we want strictly less than. So at negative 2 and 1, we determine they're equal. So we want everything between negative 2 and 1, but not including negative 2 or 1. So all values of x between negative 2 and 1, but not including negative 2 or 1, make this inequality true. So our solution set, which we'll write in both interval and set builder notations, as an interval, we would write negative 2, comma 1, and have round open braces on each side. So we'd have an open brace, negative 2, comma 1, and then another open brace. In set builder notation, we would write the set of x such that, and then to state that x is between negative 2 and 1, we'll write negative 2 less than x less than 1, and end that with a set brace. One thing to note, this open negative interval from negative 2 to 1, we know this is an interval and not a point based on context. So we know this is an interval from the context of this problem. For this last part, we'll use these two graphs again to determine where x squared plus 2x minus 1 is greater than or equal to negative x squared plus 3. So let's highlight these graphs, and I'm looking for where the red curve is greater than or equal to that blue curve. So I need it to be higher, and so I can see that it's higher from negative 2 going to the left, and I can see that the red curve is higher going from 1 to the right. So I want to label a couple things here. This portion that I've just highlighted is where it's greater than. Where they intersect, that's where they're equal. So at that point, negative 2, negative 1, those two curves are intersecting. And then over here, the part that I've highlighted going from 1 onward on the red curve, that's where it's greater than. And then again at that point of intersection, that's where it's equal. So if I again come down onto below this graph, I can see that from negative 2 going to the left, the red curve is greater than or equal to, and going from 1 to the right, it's greater than or equal to. So looking at what values of x are going to make this true, so the solutions to this inequality are all values of x for which x is less than or equal to negative 2, or x is greater than or equal to 1. So when we write that solution set as an interval, and these lines that I've drawn below the graph can help with this interval, need all values of x less than or equal to negative 2 or greater than or equal to 1. So I'll have for interval notation, I'll go from negative infinity to negative 2. And on negative infinity, I put an open brace. So I write open brace, negative infinity, comma, negative 2. To make sure I include negative 2, I put a square brace there. Then I'm going to union that, and now I'll do values of x greater than or equal to 1. So I'll do a square brace with a 1, and then a comma, and then I'll put infinity on the end with an open brace. So that's my interval notation, showing all values of x that are less than or equal to negative 2 or greater than or equal to 1. To write this using set builder notation, I'd simply write the set of x such that, and then x less than or equal to negative 2, or x greater than or equal to 1.